Sx omega can be h f x omega square of Sf omega. I call this as equation number 19. So, equation 19 gives the relationship between the response spectrum Sx omega and the load spectrum Sf omega. So, that is a very important relationship we arrived in this lecture. Further, there are some interesting features about equation 19. Equation 19 does not contain information about phase shift phi between load and the response. You can see the term is squared, therefore, the phase shift concept or the parameter is lost. So, it gives information only about the amplification of amplitude, that is very important. Let us try to understand this graphically. Let us say I have f of t which can be a signal like this on a time scale representing f of t. Let us say this is my load. I take an autocorrelation of this. The autocorrelation function typically comes like this. Say this is my C f of tau, and ultimately this will give me the plot of the transfer function in terms of omega and Sf omega, which can typically look like this. If I apply this load to a system which is a dynamic system, which has got a mass, which has got a damping force, which has got also the restoring force, and external excitation is what we applied here. If this is a dynamic system whose response looks like this on a time history, the system has a property which is transfer function, which can be this way and this can be h f x tau. The system will also have the response whose autocorrelation is given by this plot. Ultimately, the system will have a response which will get amplified for a given damping for various values of omega, which is the mod value of h f x omega. This will now lead to the response of the system in spectral ordinate, which is S x omega, which we call as response spectrum. So, this becomes my load spectrum and this becomes my response spectrum and this becomes my transfer function, which gives only the information about the amplitude and not about the phase shift between the response applied, response obtained and the force applied on the given system. In addition, mean value and variance are also important. So, mean value of the response is given by mx is h f x 0 of mf, which we already derived, and the variance is minus to plus infinity h f x 0 omega square S f omega d omega. I call this equation as equation 20. Therefore, from the response spectrum, one can compute several statistical quantities which are important for assessing the response. For example, standard deviation of the response can be readily obtained from the variance, that is from equation 20. For the response function be the response of a linear system, transfer function h f x omega applied, or let us say subjected to a stationary load process f of t, sigma x square, which we wrote earlier as f x omega square s f omega d omega, is now valid. The right hand side of this equation is to be computed numerically. Now, as an application problem to dynamical systems, if damping in the system is very small, then for damping to be very small than unity, the transfer function is very narrow. Which will be focused or which will be epicentered around the resonance frequency omega r, where omega r is omega as omega n, that is excitation frequency, and the natural frequency of the system matches. This implies a very important statement that main contribution to the integral in equation 21 comes around the interval closer to omega r. That is very important statement. Let us try to understand this graphically. Let us say I try to plot the ratio of forcing frequency to the natural frequency. Let us try to plot this closely in the range of beta equals 1, which is resonating. Let us try to plot in the y axis h omega, the absolute values we call amplitude amplification. Say this is 0.1 by k, this is let us say 1 by k, this is 10 by k, this is 100 by k. Let us say the curve starts from 1, gets risen and goes to the narrow band here and then falls down steeply. This is for zeta equals 0.01 typically. When look for other zetas, zeta 0.1, 0.5 and zeta equals 1.0. So, friends, in the above plot you can see that there is a narrow band focus, there is a narrow band focus at resonance, which is the main contribution of the integral, and h omega is simply 1 by k, the dynamic amplification factor, which we also discussed in the last lecture. Therefore, if the response spectrum varies slower than the transfer function, then it is possible to replace the response, the load spectrum by S0, which is S load spectrum at omega r. Hence, sigma x square is now going to be S0 minus to plus infinity hfx omega square d omega. This procedure of replacing the input spectrum by a constant is called white noise approximation Let us look at a typical feature of the response spectrum. Consider a weakly dampened dynamic system which will be obviously narrow banded. So, the response spectrum will become narrow banded for a weakly damped system. This will be dominated largely by h fx omega square. Hence, with the white noise approximation, sigma x square is S0 minus to plus infinity h fx omega square d omega, which is equation 22. Let us see the summary what we learned in this lecture. We are able to connect the load history to the response history of a linear system. We also said when the load process is a zero mean process, response will follow same nature. Further, for a weakly damped dynamic systems, response spectrum can be approximated by white noise approximation where the spectral energy will be epicentered around the resonance frequency only. We will continue this discussion in the next lecture by explaining more about the response spectrum. Then we will also discuss the importance and example of stochastic process in analysis of offshore structures. Thank you.